Good morning, everyone, and welcome to our webinar on applying generative AI to credit risk scorecards. My name is Krishna Mehta, and joining me today will be my colleagues Pat Bhattacharya and Shikha Agarwal. The presentation should run about 30 to 35 minutes, and we will have a question and answer session at the end. However, please feel free to use the chat board to ask questions and share your comments as the presentation goes along, and we will try to respond as soon as we can. A little bit about us. We are a data science company based out of New Jersey and have a presence in India. We use predictive analytics, machine learning, and artificial intelligence to help organizations achieve superior business outcomes. And we work in financial services, nonprofits, retail, and publishing. Here are some brands which have partnered with us over the years. Before we get into the experiment from this time, for context, let me share with you what we did last time. I will try to keep this short and just summarize our process. Uh, we started with the generative AI model, the Llama model, and fed it prompts, which were basically records from a credit application data set, and one record was, or one applicant's information was fed at a time. And the data set we used was the Australian credit card data. This is a publicly available data. It has limited attributes. Attributes are masked, but we have used that for the last time, and we are continuing to use it this time. So then we had this generative AI model, and we compared it to a credit risk model, which was developed using traditional techniques. And this was a logistic regression model. This was built to the rigor one would need to build for regulatory review. And then from the comparison, the key takeaways that we found were that generative AI did not work very well by itself. And this was not very surprising. At the end, we were not giving the model any context, and so it did not do very well. But the very interesting result from last time was that when we combined the generative AI and traditional logistic regression model, we got really good results, much better than the ones we got just from a traditional model build. Let me now give you an overview of the experiments from this time. So our focus this time was to see if we could get the generative AI models to be closer to the traditional credit risk models. So the first thing we did was provide generative AI greater context using an approach called RAG. We had seen earlier that generative AI model was not doing well when it was directly fed the prompts because it did not have a lot of context about the problem we were trying to solve. So the RAG approach provides this context, and we will talk about it in greater details later in the presentation. The second thing we did was we tweaked the last layer of the generative AI model, and using that we compared the results obtained from the traditional logistic regression model. And finally, we introduced a new class of models. These are vision models which take images as inputs, and feeding these vision models pictures of the data we had obtained, we tried to see the quality of the predictions the model made and how it compared to the large language model predictions. Let me give you some key terms and their definitions so that it is easier to follow the rest of the presentation. The first is LLM. Again, this is something probably everyone is familiar with. It's just large language model. It's a form of learning transformer model that uses natural language processing. Embeddings. Embeddings are vector representation of the prompt that has been fed to the generative AI model. Llama. Llama is a large language model created by Meta and is available for download to local systems. DeepSeek. This is another large language model which is originated in China and is again available for download to local systems. Finbert and Roberta. These are examples of lightweight large language models that are good for specific domain specific tasks. For example, Finbert works very well for financial data. Vision models. These are a class of deep learning models that take images as inputs. RAG. My colleagues will spend more time on RAG, but it provides greater context to the large language model for the submitted prompt. And so it reduces hallucination, which is the phenomenon where AI model provides misleading information largely because of lack of context. And AUC. AUC is a measure of model accuracy that takes a value between 0 and 1, with a higher value generally considered to be better. A value of 0.5 implies a random result. So with this, I would now like to hand over the presentation to my colleague Shikha, who will take you through the RAG process.
Thank you, Krishna, for handing it over to me. I am Dr. Shikha Agarwal, data scientist at Jigyasa Analytics. Problem with generative AI model is that they often lack sufficient context when generating responses, leading to inaccuracies or hallucination. To address this problem, with RAC approach, a knowledge base is created which contains relevant information to provide necessary context to the generative AI models. During execution of RAG approach, AI model retrieves relevant information from the knowledge base, ensuring more accurate and contextual outputs. So, retrieval augmented generation or RAG is an approach designed to improve the performance of generative AI models by integrating it with necessary contextual information. Now look at how we implemented RAG for credit default prediction. We started by using training data labeled with class information. Each training record is converted into embeddings, and these embeddings were stored in vector database. By end of this initial step, we have vector database which has embedding of training records to serve as knowledge base for generative AI model. So when a new records needs classification, we first convert it into an embedding, and we will perform a similarity search to get the relevant context from the vector database. So what we have done, we have a prompt, we have converted it into the vector embeddings, and we got similar prompt from the knowledge base. Then what we will create a augmented prompt. The relevant context is combined with original query required to form an augmented prompt. This prompt is then passed to large language model for classification, and large language model will analyze this augmented prompt and provides a classification result to determine whether the record will default or not. To analyze the impact of RAG, we have done two experiments. Experiment with RAG and experiment without RAG, which means direct prompting without relevant context. We have evaluated three large language models: Llama 2 7 billion model, DeepSeek Distill 1.5 billion Queen model, DeepSeek Distill 7 billion Queen model. Now let's see the performance with RAG. Llama 2 performs poorly with RAG, showing AUC score of around 0.60 on training data and 0.50 on test data, meaning it failed to learn meaningful pattern with RAG approach. DeepSeek models, however, perform significantly better with RAG. The 1.5 billion Queen model achieves the highest test AUC of 0.59 and 7 billion Queen model follows with test AUC of 0.57. Now let's see the result without RAG approach. In this approach, all the models struggles to give good results. Llama 2 model performs significantly better than before with test AUC in this case 0.59. Both DeepSeek model performs worse with AUC score below 0.5, which shows that predictions are like random guessing. The key takeaway from this experiment is that Llama 2 model performs better with direct prompting and DeepSeek models perform better with RAG approach. Now I will hand it over to Pat to present the next part of the presentation.
Thanks, Shikha. Hi, everyone, and thank you for attending this presentation. My name is Pat Bhattacharya, and let me start by giving you an overview of what we have done so far and where we are going next. In the last webinar, as well as in this one, we have been working with LLM models. We initially started with directly giving prompts to the LLM model to see how well it does. And we found that direct prompting to the LLM model does not result in good predictions. And the table here shows that the AUCs that we got from this exercise. Today, Shikha presented the RAG approach, where we provide the LLM model with a knowledge base for the relevant domain. We saw that this allowed the LLM model to provide somewhat better predictions as compared to the original model. This is especially true of the DeepSeek models, as we can see if we compare the second and third rows of the lower table to the second and third rows of the table above. For all of these exercises that we have done so far, we have used the weights of the existing LLM models and did not try to change those in any way. In the next steps, we will shift gears a bit and try to see if we can actually change the parameters or weights of the LLM model itself to further improve performance. I would like to mention here that for all of the experiments that we presented last time, as well as for the ones presented today, we followed regulatory standards. So we dropped variables from our model if they were too highly correlated with the dependent variable. The LLM models that we have been working with are pre-trained models that have been trained with vast amounts of data from various sources and contain billions of parameters. These models and their parameters or weights can be downloaded and adapted to a specific task by fine-tuning them. What this means is that we use most of the weights or parameters from the pre-trained models, but change some of the parameters using the data for our domain. This is called a transfer learning approach, which means that we take a pre-trained model and then transfer the learnings from that pre-trained model to our domain. One thing I would like to mention here is that now that we are trying to fine-tune the model, the computational requirements become much more challenging. So models have to be chosen very carefully in order to have a successful and speedy fine-tuning outcome. And that has been an important factor in selecting models for the remainder of this presentation. For most of this presentation, we have talked about pre-trained LLM models, but there are many types of pre-trained models available. There are pre-trained image recognition models, which are extremely good for image classification. Then there are pre-trained object detection models, which can be used to identify specific objects within images. And then, of course, there are pre-trained language models, which can be used for natural language processing, as well as classification tasks such as sentiment analysis. Up until now, we have focused only on LLMs. However, when looking at pre-trained models, we decided to expand the horizon and look at other types of models as well. And so we decided to also work with image recognition models. The reason for this is twofold. First, while we decision scientists most commonly work with tabular data, image data is all around us. In order to harness that information, it is important to be able to work with image models. Secondly, image-based models are very good at identifying patterns in images. So by converting tabular data into images, we can potentially extract complex relationships between features that might be harder to capture with traditional tabular learning methods. Before running our image-based models, we had to take some steps to convert our data to images. We wanted to understand how these models perform on our Australian credit card dataset, and so we used the features in our dataset to create an image for each observation. We labeled each image as either a default or a non-default based on the dependent variable for that observation, and then we finally split all of these images into training, validation, and test groups. Once we had all our images, we decided to use the ResNet 50 model for our experiments. And so we used the weights from the ResNet 50 model and further fine-tuned those weights with our training images. The reason we use the ResNet 50 model is because it is known to be a very powerful model and it performs very well with image classification tasks. I also wanted to mention here that for our earlier experiments with LLM models, we were working on the cloud. However, for these experiments, we decided to enable the GPUs within our own servers and were able to successfully fine-tune the model weights within our servers. This means that all the work can now be done in a secure environment, and client data security is no longer a concern when running these models, as there is no exposure of data to the cloud. When we work with real images and pictures of real objects, the data embedded within those images is very complex. These pre-trained image models are designed to perform very well when the data embedded within them contains lots of features and complex relationships among those features. Over here, we have converted tabular data to images, and our Australian credit card dataset contains only 14 features, and some of these were dropped to meet regulatory standards, and so the data here is less complex. This slide shows the results of the last layer fine-tuning of the ResNet model. And as we can see, that even with this limited data, the performance of this image model is not too bad. The train AUC is 0.668, the test AUC is 0.651, and the validation AUC is 0.701. If we compare that to the results from the RAG approach, we can see that the last layer fine-tuning of the image model performs better than the RAG approach, especially in the test and the validation samples. Now over here, I'm comparing the fine-tuned image model, whereas the RAG approach was applied to LLM models. And so in the next slide, Shikha will show the results of fine-tuning an LLM model, and we will then also be able to compare those results with the RAG approach.
Thank you, Pat, for handing it over to me again. To make LLM truly effective for specialized domain, we need adaptation strategies. Two methods that we have experimented are RAG, retrieval augmented generation, and last layer fine tuning. RAG I have discussed in the earlier part of the presentation. Last layer fine tuning I will discuss on the next slide. Fine tune last layer. This experiment begins with downloading the model to a local environment and preparing it for fine tuning. First, we freeze all the layer of the model and attach a classification head at the end of last layer. Next, we unfroze the last layer of the model and fine tune it using custom loss function and best model selection function on the Australian credit card data. This allowed the model to better understand the pattern relevant to our classification task while keeping the fine-tuning process manageable. Finally, the fine-tuned model was used to generate classification results. Given the computational constraints, we opt for lightweight models like Roberta and Finbert to ensure efficiency. This approach strikes a balance between computational feasibility and large language model fine-tuning. To analyze the impact of fine-tuning of last layer, we have used two models, Finbert and Roberta. They are lightweight models. Finbert outperforms Roberta across all three stages of evaluation. Finbert achieves AUC of 0.88 on training data, while Roberta is slightly lower at 0.83. Finbert scores 0.79 on test dataset, while Roberta has test AUC of 0.76. In case of validation dataset, Finbert maintained a higher score of 0.77, while Roberta has 0.73. Key takeaway from this experiment is Finbert being a financial domain specific model shows stronger performance, although Roberta being a general purpose NLP model performed decently after fine tuning of last layer on domain specific dataset. Now I will hand it over to Pat again for overall results.
Thank you, Shikha, for those most interesting results. On this slide, I wanted to pull up those results once again from the fine-tuned LLM models, as shown in this table here, and compare them to the results from the RAG approach applied to LLM models, as shown in this lower table. And we can see that the AUCs after fine-tuning the model have improved significantly as compared to when we only use the RAG approach on the LLM models. So what we understand from this exercise is that fine-tuning a pre-trained model significantly improves its performance. On this slide, we show an overall summary of all the important results that we obtained during all our experiments. In our previous webinar, the first experiment that we performed was to directly give a prompt to the Llama model, and we found that the predictions from that model were not much better than a random guess. This result is shown on this slide as case 1. At that time, we were also able to extract embeddings from the Llama model, and we used the embeddings from the Llama model to build a logistic regression model, and those results are shown on this slide as case 2. Note that in case 2, we did not use any of the original features and only used the top embeddings from the Llama model as independent variables in our logistic regression model. We found that this improved performance and the AUCs with this approach were much better than a random guess. Case 3 is where the traditional logistic regression model was built, but only with the original features and without any embeddings. We then decided to combine both the original features and the embeddings to build another logistic regression model, and this is shown on this slide as case 4. And as we can see from the AUCs, this combined model gave us the best results as compared to all the other models that were built last time. So this was the results from last time. Today, we presented the RAG approach, and this is depicted here as case 5. Case 6 shows the results of the transfer learning with the ResNet 50 model, and case 7 shows the results of transfer learning with the Finbert model. We can see that the top performing models for this experiment are the fine-tuned LLM model, which is case 7, and the traditional plus embeddings logistic model, which is case 4. Case 7 has the highest AUCs in the modeling and test samples, whereas case 4 has the highest AUC in the validation sample, although the LLM model is very close. In terms of overall performance, fine-tuning the LLM model gives us the best results. We can see from all of these experiments that the LLM model can be used to enhance our traditional logistic regression models. We can do this either by using the embeddings from the LLM models as additional inputs to our traditional models, or we can directly fine-tune the LLM models to improve their predictive power within our domain. I will now hand it over to Krishna for further analysis of the results.
Thank you, Pat, for those most interesting results and for your insights about them. What we will do next is share our thoughts on why we see what we see from these experiments. So, the first thing is, why do we see the performance improvement from prompts to RAG to tweaks? So, with simple prompts, model lacks context. It produces great embeddings because we can see these embeddings do so well in the logistic regression model. However, it does not know how to pick among these embeddings, does not know which of these are relevant for the context. And that is why it does not do as well. With the RAG, is able to get additional contextual detail from the query knowledge base. And because of that, the performance improves. Now, when we are able to tweak and adjust the weights of the last layer of the model now reflects the training data. At least the last layer of the model now reflects the training data, and hence it is most suited to give better predictions for the problem at hand. And that is why we see the gradual improvement from simple prompt to RAG to the tweaks. The next thing which we feel is that the way forward is smaller, task specific, or domain specific large language models. You see, the large language models, which are domain specific or task specific, are being built on a narrower set of data. And therefore, the scope for hallucination is less, and so the model will be more accurate. And then, because they are lightweight, they can be tweaked easily without requiring a server farm on simpler machines. That means that a lot more applications can be developed by a lot of smaller organizations, making their use more widespread. And then the third thing is that since they can be easily tweaked and run on local systems, data security is less of an issue or not an issue at all. And so a lot of sensitive data which might otherwise not be used for large language models can now be used and therefore develop richer applications. And the third thing which we feel is that image models open up these exciting possibilities for credit risk and fraud. So the image model did not actually convert the image of the data into some form of text, but worked directly with the pictures and still gave us these most amazing results. Something we did not share in the presentation, but we did some experiments where we took some of the top correlated variables uh, out of the model. And when we did that, the model's performance dropped because these variables were very highly correlated with the dependent variable. So taking them out should drop the performance of the model. But what was most amazing and exciting about this is that these statistical principles seem to carry over even when we are dealing with pictures. And think of the possibilities because of that. Think of using real pictures of assets, equipment, offices, and feeding them directly into your credit risk model, and think of the improvement one can get because of that. The last thing I want to talk to you about is what is next for us on the horizon. So, we are very excited about the results we have obtained from the vision models and are equally excited with the LLM results. And what if we could combine them? Will we get even better results? That is something we want to play around with and find out over the next few months. Now, for vision models, we have used pictures of the data. What if we could also use real pictures of assets, of offices, and other things relevant for the credit decision process? And similarly, for large language models, what if we could use other data sources? We feel that will improve the model, but that needs to be tested. And that is something we are seeking partners for. So if your organization is interested, we would love to have you on board for the next phase of the experiments. And then we want to expand our study to applications in marketing fraud as well as collections. And finally, we want to look at AI models that take audio as inputs and see if that has a role to play in the credit risk process or in some other modeling application. Thank you again for making the time for this presentation. I would also like to acknowledge my colleagues uh, Ratna Sinha and Barkha Agarwal, who did not present today but made significant contributions to this research. And with that, let us start the question and answer sessions.